In this video, I want to talk about what to do when we have a property that falls inside this mixture region of the vapor dome. So it's going to fall into this region right here. And I just want to go over how we can read property tables for this and how we can figure out what our properties are. So I've drawn a PV chart and I've drawn a TV chart. These are not to scale and they won't be to scale at any point in this video. So we have these two tables. We have a temperature table and we have a pressure table. The pressure table goes with the PV chart. The temperature table goes with the TV chart. Let's look at the pressure table first, and I've only taken a very, very, very small subset of this. This is actually going to go until about 220 bar. So you can imagine that I'm not drawing this to scale. Everything in this would sort of fall into like this region right here. So I'm just going to spread it out for visual clearness, but know that this process and what I'm doing is it goes through this entire table. So it's going to go from right here, like this 0.04 to the 220 up here. But I'm going to sort of scale this, so I'm just going to be looking at okay, this is 0.5, even though it's not really. So let's start with that. Okay, so let's say this is where 0.5 is. I'm just trying to illustrate the process. So 0.5 is right here. This next column, 81.33, tells me what my temperature is at 0.5 bar. However, we have these isotherms that look like this. This line shows my constant temperature. So this line always shows a temperature that's equal to 81.33 degrees Celsius. So that tells me right here at 0.5 bar, when I'm inside my mixture region, from this point to this point, that this temperature from here to here is constant at 81.33 degrees, and that is given by whatever this column is. So if I went up a little bit and I said this was 0.7 degrees, well, I'd have a different isobar, and at 0.7 degrees, then I would know inside the vapor dome that the temperature would be 89.95. So that would be from this point to this point along this line. And when you get into the compressed region or you get into the superheated region, you still have these lines, but they have a different shape to it. They're not constant. So if you were doing a process that was a constant temperature, you would still follow this line down. So let me get rid of this line just for visual clarity. And let's talk about the TV chart. And the TV chart works the exact same way. Again, this is not to scale. I'm just trying to show the process. But this temperature, let's look at, say, 12 degrees. Well, the temperature is along this axis right here. If we had, say, this was here, 12 degrees Celsius, then the underneath the vapor dome would be a constant pressure. And that constant pressure would be given by this value right here. So this, it goes the other way than my isotherm. This is an isobar. The isobar is going to be P is equal to 0.01402 bar. And what this means is from this point right here to this point right here, my pressure in this mixture region is constant. And this temperature, or this pressure, is 0.01402. Now, the next couple of columns that we have are, I'm going to write them just so that it's easier to see. We have a saturated liquid, we have a saturated vapor, a saturated liquid, a saturated vapor for a specific volume. We have a saturated liquid, UG, for internal energy. And we have a saturated liquid UF for internal energy, and a saturated liquid UG for internal energy. So UG, UF. We have a saturated liquid for enthalpy. Enthalpy is H, so HF. This is Hg, which is a saturated vapor. HF, Hg. And then we have entropy, so SF and Sg. Now, the enthalpy has this extra column right here, and all this column is doing is subtracting the Hg from our HF. And we can prove that really quickly. We can say, all right, this is going to be 2554.4 minus 121.46, and we'll get this 432.9, this right here. So where do these correspond to? Well, anything that has an F to it is going to correspond to this point right here. So this is my specific volume as a saturated liquid, so VF. This is my internal energy as a saturated liquid, UF. And this is my enthalpy as a saturated liquid, HF. We also have entropy. Down here, it's the exact same thing. So this would be VF, this would be UF, HF, and SF. Now, the only thing you need to be careful of, and depends on the table you use, is that VF does have this times 10 to the third. So what this is saying is this column is whatever VF is times 1,000, because it's so small. So this right here is actually 1.0360 times 10 to the minus 3. So just keep that in mind. It doesn't really affect anything we're doing right now. Now on the other side, this point is going to be our VG, UG, HG, and SG. So this point is VG, UG, HG, and SG. So we've constrained both sides, and we know what's happening on each side of this vapor dome. So it's along this line. You just need to look up a specific, a particular temperature or a pressure, and you can get all of this information. So how do we know what tables to use? Well, realistically, a lot of the times you are going to be given something like, okay, at some pressure, say 0.5 bar, my volume is going to be equal to 2.3 meters cubed per kilogram. So what you would do, you go to your table, 0.5 bar, and I'm going to look at these two numbers. Remember, so 0.5, as we said over here, this point right here refers to 1.03 times 10 to the minus third. Then we have our line that goes straight across. And this point right here corresponds to 3.240 meters cubed over kilogram. And what we do is we look to see, does this value fall in between these 2 points? And in this case, it does. Maybe it's over here. And this would be this 2.3 meters cubed per kilogram. And if it's greater than this 3.2, we know we're in the superheated region. If it's less than this 1.03, we know we are in the compressed region. So that's how we can tell which chart to use. How do we, additionally, maybe instead of given a pressure, we're given a temperature. At some temperature 12, my volume is equal to 80. Okay, so we go to 12 right here. Then we look, and 80 would fit in between this and this. So In terms of the temperature and pressure table, it will be depending on what's given. In terms of are we able to use a saturated table, a superheated table, a compressed table, or that approximation? It will depend on the values that are given. The other thing that could be given is we could be given a pressure value and we could be given a temperature value. And let's say we are given at a pressure of 0.5 bar, my temperature is 81.33. Well, what we need to do is at 0.5 bar, we need to figure out this value right here. That value is our saturation temperature. If our saturation temperature is equal to what we're given, then we know that that temperature is this line. So we are inside our mixture region. If our temperature is less than our saturation temperature, then it turns out we're in the compressed region. If it's greater than our saturation temperature, then we're in the superheated region. Turns out we can do this the other way as well. So say we were given a temperature is, let's do a different number, 10, and our pressure is 0.01228 bar. It's the same idea. If my temperature is equal to my saturated pressure, which is this right here, then we're in the mixture region. Now, it's actually the opposite condition. So if my pressure is less than my saturated pressure, then I know I'm in this compressed area or the superheated area. If my pressure is greater than my saturated pressure, then I'm in my compressed area over here. So that's how we know what table is valid, if we can use the pressure table, if we can't use the pressure table. So now let's say we have a volume. We're given that a volume is equal to 2 meters cubed per kilogram at 0.5 bar. And this will work for any property. I just happen to be choosing volume. And this can work at temperature. Say if we were given this at a temperature instead of a bar, we would use the temperature table. But let's just say we were given our example at 0.5 bar. We were said our specific volume is 2 meter cubed per kilogram. How do we know how far over it is? So at 0.5, assume, let's say I can draw a straight line. At 0.5 bar, we know that this is 1.03 times 10 to the minus 3 meters cubed per kilogram. And we know that this is going to be 3.24 meters cubed per kilogram. We know that 2 is between here, but we want to figure out how far over it is. And if we can figure out how far over it is, then we can use that piece of information to determine any other property we want. And we call this quality. We're going to call it an X. This is my quality. And all I'm trying to really do is figure out the percentage over that I am from this point of this entire distance. So the quality is going to be V minus VF. Sort of think of it as this distance right here, divided by that full distance, which would be VG minus VF. In this particular case, it's going to be V, which is 2, minus VF, which is 1.03 times 10 to the minus 3, divided by 3.24 minus 1.03 times 10 to the minus 3. And if we do that in our calculator, we will get our quality. So we get a quality that's equal to 0.617. And what this means is this is 61.7%. Now, if you're given a quality, you automatically know that you need to be in this this mixture region. But now, let's say we were also now asked to figure out what is our specific internal energy. Well, how do we do that? We know that the quality is going to be the same, and really we don't need to just use this equation. We could have used, this is U minus UF over UG minus UF. And that would also give us a quality. Now, if we got a quality of 0, that means we're right on this line right here. So this would be a quality of 0. If we got a quality of 1, that means we're right on our saturated gas line. So this would be a quality X equals to 1. But now let's say we wanted to figure out what U is equal to. And we know what our quality is equal to. So we can just rearrange this equation for U. What we'll get is we'll get that U is equal to X times UG minus UF plus UF. And we could use this equation. We could also rearrange this a little bit. We could say this is equal to X UG minus X UF plus UF. And if we group this, we'll have this is UF times 1 minus X plus X UG. This is just sort of the equation that I remember. So I usually use this one. So my internal energy is going to be UF. We need to grab those from tables. So let's do that. Let's hide this and show this. So I'll write it right here. UG is equal to 2483.9. This. UF is equal to 340.44. Now let's hide this and bring my other layer back. So this is 340.44 times 1 minus X, which is this 0.617, and plus 0.617 times UG, which is 2483.9. And we just put that in the calculator. So this is going to be 340 times 1 minus 0.617 plus 0.617 times 2483.9. And we get that U is equal to 1662.78. And if we look at our chart, 1662.78, it should, if everything's done right, be in between those two numbers.